this presentation. My name is Diederick Vermetten, and I will be describing our work on benchmarking metaphor-based optimization heuristics. What I want to start with is this notion of metaphor-based heuristics. So a metaphor is something that can be quite useful to describe complex algorithms. For example, the evolutionary algorithms are based on the metaphor of Darwinian evolution. It's an aspiration that can create new techniques. We have the well-known things like particle swarm optimization that came from originally simulating the behavior of birds. And these things lead to potentially interesting algorithms of different ways that we can approach them. But there's also a downside to this. The downside is that if you take this too far and you rely on these metaphors too heavily, this can obscure the actual algorithmic ideas that you're trying to present. And this is the case with a lot of different algorithms. And with a lot, I mean there are really hundreds of these different algorithms that have been proposed and really driven by the metaphor that they've made. And there's all kinds of ways people find inspiration, and people name their algorithms after these metaphors. We have things like hog optimizers, plant propagations, flying squirrels, also things that are not really natural per se, but things like the mind-guessed algorithm, life choice-based optimizer, etc. There's a lot of these things out there. And because there's so many algorithms and all of them are described with their own metaphor, with their own way of describing similar algorithmic aspects, this sometimes means that we cannot really see the forest for the trees. There's so much there that something might be just a clone of something else, or something might be really novel and do something that no one else has done before, but we cannot really figure it out just from the algorithm description itself. Well, technically we can, but it's very time-consuming process to really case by case look at these algorithms and see, are they the same as something we already know, or are they doing something different? So by relying so much on the metaphor, it's hard to show that, for example, an algorithm is just doing the same as ESO is doing with different terminology. And well, you can do this. I think it just costs a lot of effort. So what we do here is not go into any of these algorithms in detail, but we use benchmarking to try to find some trends within this and to see what is out there in terms of available implementations of these algorithms, and is there anything we can learn from this. So our setup is as follows. We have 4 different libraries from which we take these algorithms. And in addition to these libraries, we take several baseline algorithms. For example, things from Nevergrad. We have also some CMAES. We have random search, of course. And this gives us a total of 294 algorithms. Of course, there's a bit of overlap between these different libraries. So some of these libraries have, for example, particle swarm optimization implemented multiple times, but that gives us a way to compare implementations of algorithms with the same name or with at least the same inspiration. And then our benchmarking setup is quite standard. We have 24 functions from the BBOB suite. Dimensionality is 2 up to 20. Multiple instances, multiple runs per instance, for quite a lot of runs in total. And the performance measure we will be focusing on in our results is the area over the convergence curve, which is basically the same as the area under the ECDF. It's an anytime performance measure that we can normalize, and thus we can aggregate it across different functions quite easily. So with that set in mind, let's look at the first results. The first results are a comparison of our algorithms against the random search baseline, where we see on the x-axis we have different PQP functions, and on the y-axis we have dimensionalities. And then the number here indicates how many of the 293 algorithms are worse than random search, worse in terms of mean anytime performance. And then we see that quite a few algorithms on a lot of these different functions are in fact worse. If we look at the simplest functions, the sphere function, for example, we see there's around 50 algorithms that are not managing to outfill just pure random sampling. On the higher dimensionalities, things get a bit better for these algorithms, just because random search scales very poorly on these, if we have some decently high conditioning especially. But overall the trend is quite clear, and many algorithms are just performing terribly. We can also take the opposite approach and look at what algorithms are actually performing well, and then we get to figures that look like this. So here we have three different columns, because they are a bit long, they are put side by side. But the first column indicates how many functions, again across different dimensionalities, does the listed algorithm perform better on, or in the top 3 on with all of the algorithms in our portfolio. So how often is it in the top 3? And then we can see that at the very top here we have BiPop, which is a version of CMAS, changing population size at restart. That performs very well. And then we have some other algorithm versions, things like a lot of versions of differential evolution that perform quite well, sort of normal modular CMAS, etc. So that is measured in amount of times it's top 3. We can also look at overall loss. So each function individually, how much anytime performance do we lose by selecting this algorithm instead of the best of our whole portfolio, and then aggregating that across all of the functions, where we see that again values here start off quite low. Well, and finally we can, in the final column, look at how much an algorithm is contributing to the portfolio of baseline algorithms. So we take our baseline algorithms, they create a portfolio, and then if we add any of these other algorithms to it, how much does that improve the performance overall? So are there functions where the baselines are performing okay, but adding another one to it makes the performance get better? And then we see there are some that do indeed different dimensionalities. For example, this one can add something to it on high dimensionalities, while this one can add something to it on low dimensionalities. So there are definitely some algorithms that do contribute something different than what's already included in our baselines. That's just one way of looking at performance, aggregate over all functions with the budgets that we had set originally. We can also look at what the impact is of different factors. For example, the budget itself. How much does the budget matter? So if we look at increasing budgets, then does our relative performance compared to the other algorithms in our portfolio increase or decrease. And we can see that there's some algorithms that start off contributing very little, but gain a lot in the higher budgets, like, for example, the different CMAS versions, while some others are mostly good at low budget settings, while on the higher budgets they lose out to the most of the other ones. Comparisons across different dimensionalities and different budgets already kind of show this, but the way in which we judge an algorithm on its own is influenced by many different aspects. So we have performance measure that we use, what kind of comparison are we doing, what kind of aggregation are we doing. All of this we can change around to then lead us to different kinds of conclusions about which algorithm is actually performing the best. And if you have this many degrees of freedom, then that means that making the raw data itself available, it becomes quite important. Because if you, for your paper, you show one measure and someone else is interested in a different one, then conclusions might be quite different. So data availability is something that we should definitely promote in any of these benchmark-based analyses. There's also the question of what are we actually looking for? There's often this winner-takes-all approach where I introduce a new algorithm, so I have to show that it is performing better on average than all of the other algorithms I selected. But we can also take the perspective of looking at complementarity between algorithms. So some algorithms are good in one setting, some in the other. So looking at not the best generalists, but at different specialists, so algorithms that work well in specific settings, seeing how much they contribute to portfolios of existing algorithms is something that is worthwhile to investigate as well. One way in which you could look at this kind of performance complementarity is looking at diversity in performance space. So what we have visualized here is just one example of using our data for this purpose, where we have on the x-axis the average area over the convergence curve. So here we have BIPOP CMAS, normal CMAS, and so on. And then on the y-axis we have the distance to the closest baseline in this performance space, which is just all of our individual function performances concatenated together. So how many functions is this very different? How much difference is there over all of the functions in our suite? And then we see that we have quite a decent group of algorithms that are performing relatively okay, but are also quite different than the closest baseline, at least in terms of developments, which shows that these might be the ones that are interesting to consider in more detail. And then, while this is just a taste of the data that's there, and I invite you to take a look at the paper for more detailed explanation of these figures and these aspects, I want to now highlight a few areas of these type of benchmarking studies that mean that we should still be careful with interpreting results like this. There's a lot of problems in this domain of metaphor-based heuristics, and one of them is definitely this underspecification of algorithms. So as I said before, there might be different implementations of the same algorithm, and that might be the case that someone proposes a new algorithm, but it turns out it's just a variant of an already existing algorithm. But it's also can be the case that we take the same algorithm, but it's not described in enough detail, and there's no code available. So the same algorithm becomes very different with two separate implementations, which is the case for quite a few algorithms that we found in our benchmark study. So this is another reason to say why code should always be public, because descriptions in papers are just not sufficient for this. But there's a real zoo of different optimization algorithms out there, and many, if not most of these, are not very useful. And while we could go one by one through these algorithms and see what their actual contributions are and what they add over existing algorithms, that is prohibitively expensive. So benchmarking might be a good in-between there, because there might be interesting obscured algorithmic ideas present within this larger set. But that, of course, still leaves a lot of questions for this and other benchmark studies regarding things like how do we judge an algorithm's contribution to an existing portfolio, and as an extension of that, how do we say whether an algorithm is novel? Can we say something about novelty based on just this data alone? Are these algorithms specified well enough so that we can reproduce them? Is the code actually matching with their descriptions? Are they tuned for the benchmark in some way, or are they really independent? And all of these are questions to answer if we want to be able to take this kind of data-driven approach to identify useful contributions, not just in this set of algorithms, but in newly proposed algorithms or different